Hello everyone and welcome back. So we're going to do a few problems with weight this time to see if we can figure it out. So let's keep on moving forward. So this problem, it says rank the following from largest weight to smallest weight if all the objects were moved to Earth. And it gives you the gravity on the moon, it gives you gravity on Mars, and it gives you this. So think about it for a second. I'm going to stare at you for a moment while I want you to think about this. Can you do this? You can. And the answers are, from largest to smallest, is B, C, A. How do I know that? It's a trick question. You don't actually need to know this. This is extraneous information. You don't even need to know what the gravity on Earth is. All you need to remember is that weight is equal to mass times gravity. They're all going to be multiplied by the same gravity, so therefore weight is proportional to mass. So the most massive object will also be the heaviest on Earth, because we're moving all of these to Earth. Same gravity, different masses, weight's going to be proportional to mass. So this one has the biggest mass, it'll be the heaviest on Earth. Second biggest, and then finally third biggest. It's one of those trick questions. And this is an important little detail. A lot of these problems are going to give you way too much information. And when it gives you too much information, you're going to get stuck. You're going to think, wait a second. Oh, yes. And you're going to make bad assumptions. Like perhaps you did here, we're thinking, I need the gravity on the moon, I need the gravity on Mars. You didn't actually need that. Now, if we ask which one is the heaviest on their different planets, on Earth, on Mars, or the moon, moon's not a planet, you know what I mean? Then it would have mattered what the gravity was, and then it would matter what the mass was. You have to take into account both. If they're all moved to Earth, it's not that hard. B, C, A. Covered and over, but you can take my word for it. Okay, let's try another one. So once again, this time we're going to say halfway between Earth and Mars. It wants us to figure out the mass of this TI-30X calculator when it's halfway between the Earth and Mars. So think about it. Okay, units of grams. You're believing in yourself, you're working on it, you're doing it in your head. You can pause the video. This is a video. I mean, I can't actually tell how hard you're working. Maybe you're just waiting for me to finish it. I'll move on. Okay, so remember that weight equals mass times gravity. So let's go ahead and calculate its mass on Earth. So mass would be equal to weight divided by gravity, which would be, for this problem, we don't even need to do that. We don't even need this equation at all because it's given it to us in pound force. And on Earth, and only on Earth, and only when it comes to weight, we can use that pound force and pound mass have the same value. Not the same unit, but the same value. So it'll have a mass that's equal to 0.25 pound mass. And we can convert that if we want to kilograms, because 1 kilogram is 2.205 pound mass. And there are 1,000 grams in 1 kilogram. So if I plug this into my calculator, what I get is 0.25 times 1000 divided by 2.205. 113.3 grams. Okay, so it's going to be 113.3 grams. Now we're moving it halfway between Mars and Earth. But does that matter? For mass, your mass is constant. It doesn't change if you move somewhere else. Your weight does, your mass does not. And so the answer will still be 113.3 grams, or 113 grams if they round it. And if I move my head out of the way, 113. Woo! So be careful. They will try to trick you. And by they, I mean me, because I'm the one who chooses your problems now. I don't try to make it too mean, but I will try to trip you up a little bit because I need you to think. It can't be just perfectly easy. There sometimes has to be a step that you have to realize, wait a second, I made a jump there and I shouldn't have. Okay, one last problem. An object has a mass of 500 kilograms on the moon, where gravity is 1.62 meters per second squared. Find the weight of the object in units of pound force on Earth, where gravity is 9.8. Now, I hate that they use 9.8. It should be 9.81. Your book is approximating a little bit too much, in my opinion. Okay, but with that, what is the weight going to be? Well, first off, let's calculate the weight on Earth in newtons. We have kilograms here. We have an acceleration in meters per second squared. That's all we need to get the weight in newtons. So if we do that, I go ahead and say 500 kilograms times 9.81 meters per second squared. And I'm going to pull up my calculator again because I am terrible at doing mental math. 500 times 9.81, 4,905. Okay. 4,905 newtons. And then we can convert that to pound force because we know that 1 newton is 0.225 pound force. That's from the front cover of your book. Anytime I have a conversion, I'm always taking the ones from the front cover of your book. So we'll convert this to pound force. So bring it up again. 4,905 times 0.225. It's about to be 1104-ish pounds. 1104 pound force. And that should hopefully be the right answer. Let's find out. And they get 1102 because they use 9.8 instead of 9.81. I'm more correct this time. Don't make me feel bad, PowerPoint. So 1104. And they did it just like we did. They calculated the force in newtons, and then they converted that force to pound force. And we also, interestingly, could have just converted this straight to pound mass, and then the whole thing where for weight, and only on Earth, pound mass and pound force have the same value. So if you multiply 2.205 by 500, it will actually pop out as that same number. Little shortcut there. Shortcuts are fun. Okay, well, I hope this helped you. Some more examples on weight. If you need more examples, please email me. I will do more. I'm happy to do more. I'll see all of you later. Bye-bye.